Okay. Then I need to turn off this one, huh? That's stopping. Okay, very good. So welcome to this, I guess it's the 7th lecture today. Now finally we can actually meet each other and do it here on campus. So we will have the lecture today, tomorrow, on the Monday here on campus. And of course, whenever you have questions, now we can look at details also in the break. So use maybe whenever necessary, use this time to talk and interact. What I would like to say is that last time actually there was a mistake in my notes. Some of you may have seen it. There was this term here, this square root in the derivation of the v velocity, which in the previous lecture, when I wrote it, was outside of the derivative. This should be inside the derivative. So I updated or I corrected the lecture notes which are online. So they are correct, but if you base it on what you have written last time, then it would be switched. So this is just to note that there was a slight mistake. The reason, of course, is obvious. There is a derivative with respect to x, and of course here is an x, so you cannot just take it out. So you actually need to take it. You need to do this derivative for the product rule in order to get the also the final result. Okay, it was just a kind of. To correct that. Okay. So, but now for today, I would like to start as usual with a short summary of what we have done last time, and then of course continue with the new material for the next 3 hours. So we have been talking about the boundary layers. So we started with the first lecture on boundary layers last time, and of course the first question is, what is really a boundary layer? Essentially, the idea is the boundary layer. If you think now of this this wing here, or any bluff body that you would have in a flow domain, the boundary layer is a thin region around that body, which is that region in the flow where viscosity is actually relevant. Viscosity is not relevant when you go further away from the body. There you can use the Euler equations. You can solve with an implicit solver, but close to the wall. Viscosity is in that sense relevant that you need to fulfill the viscous boundary conditions, which of course means the no-slip boundary conditions, for instance. So all the sharp changes of the velocity that are due to viscosity are happening in this thin boundary layer. So that means in this region you need to do a viscous solution, so it's not potential flow, it's not Euler that you can use, but the good thing is it's really only confined to a very thin region. And I guess the main aspect with boundary layers is that the thickness of the boundary layer is much, much smaller than kind of the length of a body in such a domain. So that means that delta over L would be much, much smaller than 1. That's really the approximation that you use, which you then put in the Navier-Stokes equations, and then you can do the boundary layer equations, so the Prandtl, I guess it's the Prandtl approximation here that everyone can do. And in this way, you actually change the type of the equations from hyperbolic to be a parabolic problem, which then is much easier to solve, because you can actually do marching algorithms. Okay, so this is the boundary layer, and the idea was in the last lecture how to calculate the boundary layer, or how to calculate first the growth, the thickness of the boundary layer, and then also start to look at some profiles in the boundary layer. And the first step is exactly talking about this thickness, so this delta here, and we defined 3 different types of how you could characterize the thickness. One would be delta 99, which essentially is just that position, that vertical position that corresponds to the position where you have reached 99% of the free stream velocity. We have then introduced delta star as the displacement thickness and theta as the momentum thickness. And last time we also looked at some physical reasoning behind these thicknesses, in particular for the displacement thickness. I guess the name already says it all. It quantifies the effect of deflection or displacement that this body has compared as if you would solve it with an implicit solver. And then another important thing that we introduced was the shape factor, which is just the ratio between delta star and theta. And as we will see later today, this is also an important quantity that kind of characterizes the state of the boundary layer. It's about the fullness and the stability of the profile. We will talk later about this. Yeah, and then we actually started to solve for the boundary layer profile. We did this with a similarity solution or a similarity approach, as we did also for the Stokes first problem. And I guess we don't need to go through all this derivation again, but the basic idea was that we could write everything, or the whole boundary layer equations, in terms of this f prime and f double prime, which is our similarity function. And when we do this, we get this differential equation, which is a little bit difficult to get or to obtain, but in the end, it's just basic, derivatives and integrals. But the main point here is that we then had three different coefficients, G1, G2, and G3. And now the idea was we need to choose those in such a way that they actually become independent of x and y. And as soon as they do that, then we have a true similarity solution, so a solution that can be scaled in the sense of a self-similar scaling. Yeah, we did then the first version of that by doing the Blasius, or redoing the Blasius solution. The Blasius solution was obtained in 1908 for the first time, so roughly 100 years ago. And it's essentially the solution for a zero pressure gradient flat plate boundary layer. That means it's for the case when the velocity, or where you have a constant free stream velocity, so that your velocity in the profile can just be written as f prime times this u infinity, which is a constant. And in that case, we could then see that this general equation reduces to a quite simple ordinary differential equation, non-linear though, which means it's a bit difficult to solve, but it's in principle a very easy equation. And this, or the solution to this equation, would then give us f prime, and f double prime. And with the knowledge of this f, we can then calculate our profile in terms of u, v, vorticity, and so on. And I guess that's where we got last time. So I also told you that the solution to this equation is typically done numerically. There is no closed solution, so we cannot just go in and integrate it. We use typically numerical methods. That can be normal Rongi-Kutta integration methods. And I uploaded on the homepage two different versions of solutions to that. One is a MATLAB version, which uses a kind of a general MATLAB solver for nonlinear equations. And then I uploaded also yesterday a Python-based solver or method, which is simply based on the Rongi-Kutta integration together with the sheeting method. So if you're interested, you can look at that. But the main point is, if you then run this, and actually I could even show it to you, if you would like to see that very quickly. So I have it open here. So this is the code in MATLAB that I have uploaded. It's just called Blasius.m. And it's very short. Essentially, it really just uses the nonlinear solver for MATLAB in fsolve, and internally it uses an integrator using ODE 4.5, which is a specific method to integrate the equations. And essentially, using this method, you just integrate this differential equation. When you run this in MATLAB, so go here to the command window. So if I just run this, what I will get is my solution here. So what I get then is a solution like this, where I have in black f, in red f prime, and in blue f double prime. And you can see this this behavior. So you can just download this from the homepage and run it yourself. I have here again the same picture, so we can now look at that a little bit in more detail. What this really shows. So first of all, of course, you can see that really f prime is the derivative of f, and f double prime is then the derivative of f prime. But now the question is, what do these different lines really mean? Well, to forward back again. So if you go back to the to our derivation, which was written here. So for instance, you can directly see that the velocity u, so the streamwise velocity profile, essentially is just u infinity times f prime. So that means that the red line here, that is really the mean or the velocity profile that you would see in the boundary layer. And of course, that's exactly kind of also reasonable. It starts at 0 here, and it goes to a constant free stream. That's all. So that means, I guess it's pretty clear that f prime, the red line, would just be u divided by u infinity, and all the boundary conditions that can make sense. Now, of course, you can wonder what is f and what is f double prime. F, if you now think back to what we did last time, f is actually related to the v velocity. That's exactly where I made the mistake last time with the term that was inside the derivative. But f essentially gives you, or is part of the v velocity. So I would write here just that this is related to the v velocity. F double prime, on the other hand, which is the first derivative of f, that of course means that it's somehow related to the stress. So it's somehow related to du dy. And of course that means that it also is related to the skin friction, so the CF, the skin friction coefficient. But in general, we can just say it's related to the stress that we have in the boundary layer of our velocity profile. We'll go back to that later today. Okay, so that means once we have this solution, we can calculate essentially everything that we want from our or in our boundary layer. And in particular, we can now go back and also calculate these quantities that we have discussed here, all the integral thickness quantities that we were interested in. So how thick the boundary layer is, what is the shape factor, what is the momentum loss thickness, etc. Now, because we have an analytical, or actually it's not an analytical description, it's a numerical description of the profile, but we can really go in and do all these integrals that are necessary. So let's look at that. So first of all, I guess the easiest one would be to calculate delta 99. And we can directly do that kind of visually a little bit by just looking at this. Delta 99 would be the position where we have reached 99% of the velocity. So essentially it's that point where the velocity profile has reached 0.99. And then it would be this position here, or that thickness. So this here would correspond to delta 99. And of course now this we did optically, but we can of course also do that directly in MATLAB. And it turns out if you do that, you get a value of 4.91 of this eta, or this delta, the capital delta, which is nu times x divided by u infinity. Or of course, this is 4.91 times the Blasius delta, the thickness that we introduced last time. So this is the first thing that you can directly see. So you know now the boundary layer thickness is 4.91 times this delta. In a similar way, you can also now calculate, for instance, delta star. So we know the definition. This was the integral from 0 to infinity of 1 minus u divided by u infinity times times dy. So that's the vertical integral. And of course, this we can now directly translate to our similarity solution. So that becomes delta times the integral from 0 to infinity of 1 minus f prime. And this is now in d eta. You see that I went from dy to d eta. when I also introduce this delta here to compensate for the inner derivative. And of course, this I can now calculate analytically, more or less, from knowing what f prime is as a function of eta. And if I do that, I will get a value of 1.7208 delta. So that means if I go in now, again in this view here, I can see that my displacement effect would be somewhere around here, or my displacement thickness would be somewhere around here. So this would be delta star. Of course, in practice, this would mean that this area and this area, they are the same, so that we can kind of switch them over. So that was the whole definition of delta star. And similarly, we can also calculate theta, which would be the integral from 0 to infinity of u divided by u infinity of 1 minus u divided by u infinity y. And of course, also this I can write now in terms of f, which would be delta times the integral from 0 to infinity of f prime of 1 minus f prime d eta, which becomes then, actually, if I evaluate it, 0.664 times delta. Also, that will be a very important number, as we will see in a second. Now, I would like to make one comment that this and this evaluation of these integrals, now I said that we just integrate them numerically based on the solution that we have. That is one way of doing it. You can also actually calculate it. You can do some more analytical work yourself. So, for instance, in this particular case, you can actually see that I can actually do this integral. I can do an integral of f prime analytically because I know f, so I can just integrate that. So if I do that properly, I will actually get as a result eta minus f evaluated at infinity. So that would actually be this value. So in the end, it will be this 1.728 will be the difference of f and eta. Eta would just be kind of a straight line with, eta essentially. And in the MATLAB code, this is actually done in both ways, so you can see that. Also for theta, if you go in, you can realize that you can also rewrite this. And what you will get as a result is actually even simpler. This will be just 2 times f double prime at 0. That's a little bit more complicated to derive that. You actually need to go into the Karman integral equation. But you can do that, and then in the end you will get this as a result. And also this you can see in the MATLAB code. Okay, so we have now ways of evaluating the thicknesses for our Blasius profile. Now, of course, that also means I can evaluate the shape factor. So this ratio of delta star divided by theta, which essentially is, of course, just this number divided by that number. And that becomes 2.59. And I can also evaluate kind of different type of shape factor. I can divide delta 99 with delta star, so essentially 4.9 divided by 1.7, and this gives me a value of 2.85. Okay, so I mean I can do all of this. There's perhaps 3 numbers or 2 numbers that are relevant that you may need to kind of remember. The first important number is actually this one here, and this is approximately 5. So that means delta 99 and the Blasius length scale, this delta, are different by a factor of 5. Or to put it in different words, delta 99 for the Blasius boundary layer is 5 in terms of delta. So this is one number that you should keep in mind. And the other number that is good to remember is actually this one here. So the ratio between delta 99 and delta star, which is approximately 3. You don't need to know the 2.85, you need to know the 3. So that means for a laminar boundary layer, the displacement thickness is a third of the boundary layer, of the total boundary layer. So this is kind of what you need to remember from all of these numbers. Okay. Now that we have all of this, I guess the next question would be, what is the friction in this boundary layer? So what is the shear here? Because with this we can then start to estimate what would be the shear stress or the total force that you would have if you have a flat plate moving in a fluid. And of course now, knowing the profile, this is actually not very difficult to calculate. So the friction, tau W, the wall shear stress, is simply mu times du dy evaluated at the wall. That's just this. And of course now with our profile, we actually know what that is. So du dy can actually be written as d dy of u infinity times f prime. And of course this becomes u infinity times d eta dy times f double prime, doing that properly with all the chain rule. And that becomes u infinity times the square root of u infinity times mu x times f double prime. So if I put everything back, I will get then for my wall shear stress, which will be mu times u infinity times u infinity mu x times f double prime of at 0. So this was only du dy, but now I would like to evaluate du dy at the wall. And of course now I see I have a viscosity here, I have a viscosity here, so kinematic and a dynamic viscosity. So in the end, this will just mean that the density remains. I can have my u infinity squared. So that means I'm taking out one u infinity from the square root, or I move it from the numerator to the denominator. So I get mu divided by u infinity times x times f double prime at 0. And of course this is now nice, because this guy, this is something that we know. This is a Reynolds number. So this would be Reynolds x. Or actually it would be, need to be now more exact. I mean, this will be the Reynolds number, an inverse Reynolds number. So that means at the very end I get rho times u infinity square times 1 over, like this, times Reynolds to the minus 1/2 times f double prime at 0. So this is now my wall shear stress, just calculated based on the Blasius profile. And of course, if I want to have this in non-dimensional form, so in form of CF as we introduced earlier, which is just tau W normalized with 1/2 rho u infinity squared. But now you see if I do that, then this guy here would, or these terms would disappear. So then simply get 2 times Reynolds x to the minus 1/2 times f double prime of 0. And of course, this is now a useful result, because now I know what the shear stress is in a Blasius or in a zero pressure gradient turbulent boundary layer. Because I know actually this number. This number is just f double prime at 0, and I can just go into my code or into my solution and actually look, what is f double prime at 0? This turns out that this is 0.33 roughly. So that means that actually 2 times this would then become 0.664 times Reynolds x to the minus 1/2. So this, of course, is a very strong result, because it tells me that at any point in my boundary layer, my local CF is 0.664 times Reynolds x to the minus 1/2. And we have derived that just based on the boundary layer equations. We did the Blasius solution, then we did the evaluation of the gradient, and now we have this result. And of course, that was what Mr. Blasius actually did when he derived it for the first time in 1908. And of course, therefore, this is also called the Blasius friction law for a zero pressure gradient laminar boundary layer. And of course, why is this so important? Well, because now we can really plot this. So we can plot as a function of Reynolds X, we can plot CF, and it will look, something like this. If this is actually done in log, so it's a log-log plot, then of course this power law would then become a straight line, and we know that the friction would then vary essentially along this line. So Reynolds X to the power of -1. Just to give you some numbers here as well. So for instance, if this is 100,000, then the corresponding friction would be 0.002, something like that, just to give you one value on this line. Now, of course, the point now is, this is a laminar boundary layer, and as we all know, or as we have discussed earlier, a laminar boundary layer would not stay laminar all the time, because at some point we actually may have transitioned to a turbulent state. This is what we discussed earlier in the course. So that means that at some point you would actually, let's do that in blue, at some point you would actually have an increase of the friction when the flow becomes turbulent, and you would actually go to another correlation as we had for Couette and Pipe earlier. And in boundary layers, this is then something which is typically proportional to Reynolds to -0.2, so -1/5 or so. So the slope is a little bit lower, and the friction therefore is also a little bit higher. And also, just to give you another kind of a point on this line, this here perhaps would be somewhere around 400,000, and a representative value for CF would be 0.004, kind of a doubling of the friction that you would have compared to the laminar. But this line here, that's really the beautiful thing. This line here is really what we could derive now based on the Blasius solution to the boundary. And I really think this is a very strong result, that we could actually do that completely analytically. And just as a side note here, I'm also writing down one useful turbulent correlation, so which kind of complements the Blasius friction law, would be something like this: 0.0576 times Reynolds X to the -1.5, 1 divided by 5. That would now be for the CF for the turbulent case. Okay. So one last thing I would like to mention regarding the friction. So now we have written down the friction law from Blasius as CF being something as a function of Reynolds X. There's actually one interesting connection we can now do, simply by recognizing that this here is 0.664. Somehow, I think this value we have seen before. If you now go up, you actually see there's the same value here. And actually turns out it's also related to this F double prime at 0. Of course, that's exactly the same that we have here. So this indicates that there is some connection between the momentum loss thickness, so theta, and the friction. And of course, this connection is not just a coincidence. Of course, the idea of momentum loss is exactly a measure for the friction that you would have, because that's, if you have the boundary layer losing momentum because of the growth of the boundary layer, of the action of the no slip boundary condition, that of course is exactly what in the form of a force balance is what causes the friction at the wall. So momentum loss and friction are, of course, two sides of the same thing. Now, in this course, we'll not go through the derivation, but there is actually, we can say via the Karman integral equation, one can derive the following. We have CF being the same as 2 times d theta dx, which then becomes theta divided by x. So this is a relation which tells you that CF actually is related to the change of the momentum thickness. And because we know how the momentum thickness changes as a, the typical 1 over square root of Reynolds, we can then replace this by theta divided by x. As I said, this is done by the Karman integral equation. We're not going to do the derivation here, but I will put, it's just 1 page or 2 pages maybe. I will put the derivation on the home page if you're interested, so you can look at how this is built. But in the end, it essentially explains why this 0.664 appears here in CF, and it appears also in theta in the momentum. Okay, so now we have done all of these derivations. I guess the question at this point is, how can we actually use this? So how can we use this boundary layer concept? So what can we actually do with this? Of course, now one of the things that we did, we derived the friction. Okay, I mean that's very good. But if you're really interested in calculating the flow around a wing, let's say, so you have a wing profile, something like that, and what you're interested in, you would like to know how the streamlines would look like. How would you now use this boundary layer concept to actually do something? Well, so if you now assume that you have kind of a free stream velocity u infinity, so the main point is that what you would expect to happen is that if you have this flow around an airfoil, you would of course have something growing here, this boundary layer growing, it gets thicker and thicker. This delta will get bigger and bigger. But when you start this calculation or the consideration of this body, you would actually not know how thick this boundary layer is, or how this is actually developing. So therefore, using this boundary layer concept, you would actually start to have an iterative process, in a sense that in the first step, you would just assume there is no boundary layer. I mean, you don't know what the boundary layer is, so there is not really anything you can assume, so you just say it's 0. And then you would use an inviscid method. An inviscid method could be potential flow. It could be Euler, and a solution to the Euler equations, whatever you would like to have, to just calculate the flow around this airfoil. So use inviscid method to calculate the external flow. So essentially these streamlines, if you assume that there is no boundary layer, what you will get with that is, of course, you can then calculate a pressure distribution using Bernoulli, for instance. So you get a dP dx. Of course, that would probably tell you that in this region here, dP dx would be lower than 0. So you would have what we call a favorable pressure gradient. You have an acceleration of the flow. And then, towards the end, you will have a dP dx, which is larger than 0. So that you would be in a region that is called an APG, adverse pressure. So using an inviscid method, you would get dP dx, and of course with this, and you can then also calculate the free stream velocity. UE of x. So how fast the flow is. But now you actually know the boundary conditions here locally for calculating the actual boundary layer that would develop under this pressure distribution. Because keep in mind that the normal component of the boundary layer equations was just dp dy being 0, right? Meaning that the pressure in the free stream is directly felt at the wall in the same way. So that means, so the second step now would be to solve the boundary layer equations. The boundary layer equations for this specific pressure and velocity distribution. So for a specific dp dx that we have just received or calculated, and this specific UE of x. And you solve these boundary layer equations to essentially get afterwards a value, so to get a value particular for delta star, so the displacement thickness. Because again, if you think back, the displacement effect of the boundary layer is actually what is felt from the external flow. I guess now it becomes clear what the third step would be. Once you have this displacement thickness, you would then modify your geometry, essentially making your geometry thicker by the value of delta star, so by this displacement effect that the boundary layer had. So we modify the geometry to make the profile thicker with this delta star. And then I guess the fourth step is now clear. It just means go back to step number 1. Because now we have a new geometry which is now modified by the boundary layer thickness. So now we can go back to use an implicit method to calculate the external flow. We get a pressure gradient, free stream velocity. We modify again, or we calculate first the boundary layer thickness, displacement effect, we modify and go back. And then we just do this iteration up to the point that we actually have reached a converged state. So when there's no change anymore in this update. And once we have done that, then we have solved the free stream with an implicit method and the region close to the airfoil or the bluff body with a viscous solver with the boundary layer solution. So that's kind of the idea of how you would also use this idea from Prandtl that you say viscosity is only in a thin layer and outside it's actually implicit. So we have actually now included that in our algorithm. Of course, there's one problem here, or maybe it's not a problem, but there's one aspect that we have actually not talked about. What I'm saying here, solve the boundary layer equations for specific dp dx. We have only solved it for one specific dp dx so far, which was the Blasio solution, where dp dx was actually 0. So we have only gotten now a profile for one case. But here, of course, you would need to be able to solve it for both a favorable pressure gradient and an adverse pressure gradient. So you would need to be able to solve it kind of for varying pressure gradients. So that actually means that we need to have a method, or we need to understand how would the boundary layer profile look like if we have non-zero pressure gradients. So far, we only considered UE of x is constant. This U infinity that we talked about. So now the question is, the obvious question is, can we also find solutions for pressure gradient, boundary layers? So, for instance, APG or FPG boundary layers. Can we do that? And if so, in what way, or how would they look like? And of course, I wouldn't ask this question if it was impossible. And there is actually one specific family of solutions that are quite useful when it comes to pressure gradient boundary layers. And that is the family of the so-called Falkner scan boundary layers, the Falkner scan flow. And that is something that was introduced in 1930, so roughly 20 years after the first solutions by Blasius. And it was introduced as a generalization of the Blasius solution. And it goes back to two people, I mean Falkner and Scan. It's V.M. Falkner. Actually, I tried to find out what the first name of Falkner is. I couldn't find it, so I don't know. But for Scan, I actually know it. She's called Sylvia Scan, and she also lived 1897 to 1972. Actually, you start to realize that now all these developments are not so long ago anymore. And people, they may have died 50 years ago or so. But it's kind of recent developments that we're looking at now. So anyway, Falkner and Scan, they were working together, doing this Falkner scan flow. Actually, boundary layers were not, or it was not really pressure gradients that they were interested in. The whole thing started with something that's called a wedge flow. So that's what they were looking at. A wedge is kind of a thing like that, where you have the flow coming like this. And they were interested in knowing how, this wedge, when the angle is not zero, so it's not a flat plate anymore, how this wedge would then change the properties of the boundary layer. So therefore, what they did is they considered different angles of this wedge. And what they introduced here is, this is again just notation, but they introduced this angle to be pi times beta h. Now, let me explain. This beta h, this is the Hartree parameter, and it's essentially it's the angle divided by pi. So a 90-degree angle, which would be pi half, would be a beta h of 1/2, for instance. And this Hartree parameter goes back also to a person, Douglas Hartree, and also he was living 1897 to 1958. So it was this wedge flow, and of course now, because you can assume that there is a symmetry here in the middle, you can of course say this is also it's the same solution as the flow that you would get over a ramp, just because of the symmetry here. And if you consider it as to be a ramp, then this angle, which is now half of the wedge angle, would be pi half times beta h. So that's just important to keep in mind, when you talk about these definitions. It comes from the wedge, that's why it's the Hartree parameter is the angle of the whole wedge. But if you look at it as a ramp, it's just half of the angle. So anyway, also here, it would just be the flow on top of this ramp. Okay. So now what does it, or how did they actually come up with this Falkner scan solution, or what is the difference to Blasius? Well, if you recall Blasius, the flat plate when the angle would be zero, there we defined our eta, our similarity variable, as a constant times y times x to the minus 1/2. That's the result that we got at the end for our similarity variable. Now the idea with Faulkner's scan is to actually make it more general. So they were considering that eta is very similar in Blasius. It's again c times y times x, but now they said instead of just focusing on one specific exponent minus 1/2, we just let this this exponent to be free. So they introduced this free exponent, and of course now we directly see that a is being minus 1/2 for Blasius to make this correlation. Okay. I guess now it's 4 o'clock, so we have 50 minutes break, and then after the break we will continue to see what is now really the connection of these wedges to this exponent, and then also try to derive what the solution could be for the Faulkner scan boundary. Okay, but then thank you for this first hour. I'll stop the recording. This one.